On page 709, we just have one learning target. We're going to find measures of inscribed angles and their intercepted arcs. Now, we've found measures of central angles and their intercepted arcs before, that worked out real easy. The measure of the central angle and the measure of the intercepted arc are the same. They're equal. So let's see how this one works out. On page 709, let's figure out what an inscribed angle is. An inscribed angle has a vertex on a circle and sides that contain chords of the circle. So an inscribed angle is an angle whose vertex is on the circle. Okay? Now, contrast that with a central angle. In a central angle, the vertex of the angle is the center of the circle. In an inscribed angle, the vertex of the angle is a point that is on the circle. All right? So in this drawing here, angle QRS is an inscribed angle because its vertex, point R, is a point on the circle. An intercepted arc has endpoints on the sides of an inscribed angle and lies in the interior of the inscribed angle. So, arc QS is the arc intercepted by that inscribed angle. All right? And then it goes both ways. If you have an inscribed angle, it intercepts an arc. If you have an intercepted arc, then you can, and it may not be drawn, but you can draw in an inscribed angle. And then it says there are three ways that an angle can be inscribed in a circle. And it works this way. It's all based on where the center of the circle is. The center of the circle can be on one of the sides. The center of the circle can be in the interior of the inscribed angle, or the center of the circle can be in the exterior of the inscribed angle. They're all called inscribed angles. Why? Because they fit the definition. The vertex of each one of these angles, here, here, and here, is a point on the circle. And the moment we've all been waiting for. If an angle is inscribed in a circle, then the measure of the angle equals 1/2 the measure of its intercepted arc. So the measure of the inscribed angle is not the same as the measure of the intercepted arc. The measure of the inscribed angle is 1/2 the measure of the intercepted arc. Okay? So if the measure of the intercepted arc is 100, the measure of the inscribed angle is 50. If the measure of the inscribed angle is, let's say, 30, then the measure of the intercepted arc has to be 60. Okay? Got that relationship? And it's an easy one, right? The trouble begins if you start confusing it with the relationship that a central angle has with an intercepted arc. So, inscribed angle, its measure is 1/2 the measure of the intercepted arc. And they give us some pretty easy questions to work with this. On page 713, now I don't want to mislead you though, they're not going to always stay easy. We start off with some easy ones, okay? So, on number 1 here on page 713, this is part of your assignment, so write it down. They want us to find each measure. For number 1, that's the measure of angle B. Well, angle B is an inscribed angle. I know that it is because B is on the circle. So the measure of angle B is 1/2 the measure of its intercepted arc. So the measure of angle B is 1/2 of 60. That's not so bad. Now look at number 2. This time they want us to find the measure of arc RT. Now, angle S is an inscribed angle. I know that it is because point S is on the circle. So the measure of the inscribed angle is 1/2 the measure of the intercepted arc. Well, 63 is 1/2 of what? 126. Don't take 1/2 of 63, right? 63 is 1/2 of what? Or, I mean, I'm ignoring the obvious, I think. If the inscribed angle is 1/2 the arc, isn't the arc 2 times the inscribed angle? So 2 times 63. And on this one, bit of a trick question. They're not asking us the measure of that arc, are they? They're asking us for the measure of that arc. That's okay, because look, that's a diameter because it goes to the center. So the measure of the red arc and the green arc put together has to be 180, doesn't it? That's a semicircle. Well, so what's the measure of the red arc? What's 57 times 2? 114. So can't we just subtract 114 from 180 to find the measure of the arc they tell us to find? And what is 180 minus 114? And there's the measure of arc WX. So that's still not a very difficult problem. But having said that, it's also one that's easy to miss, isn't it? Because, you know, you get in the habit of saying, okay, they're just asking us to double this, and then all of a sudden they've asked you for a different arc. So you got to really pay attention there. All right, so far so good? All right, number 4. The diagram. And see, now this one's hard, right? Because it's a word problem, so it must be difficult. That was attempted sarcasm. The diagram shows how light bends in a raindrop to make the colors of the rainbow. If the measure of arc ST equals 144, so arc ST 144, what's the measure of angle R? Well, angle R is a point on the circle, so angle R is an inscribed angle. So what's the measure of angle R? 72. It's half the measure of its intercepted arc. So the measure of angle R equals 72. So even though that was a word problem, it still wasn't all that bad. Okay, well, let's see what comes next. Two inscribed angles that intercept the same arc have a relationship. And here's what it is. The theorem says if two inscribed angles of a circle intercept the same arc or congruent arcs, but let's just stick with the same arc for a moment, then the angles are congruent. So pretend that in this figure that those aren't marked as congruent angles yet. See how angle B and angle C are both inscribed angles? They both intercept arc AD. Well, think about it. Aren't they both then, or aren't both measures then half the measure of arc AD? And if they're both that, then they got to be congruent to each other. Let me throw some numbers up here and it gets easy. If the measure of that arc is 100, then the measure of the inscribed angle is 50. So the measure of angle B is 50 because angle B intercepts that 100-degree arc. The measure of angle C is 50 because angle C intercepts that 100-degree arc. And if both those inscribed angles are 50, they're congruent to each other. So that's not a proof, that's just an example of the fact that if two inscribed angles, or actually 3 or 4 or 15 inscribed angles intercept the same arc, then those inscribed angles are congruent to each other. Okay? And let's see how we can apply that. Number 5. They want us to find the measure of angle H. Now, you got to be able to trace things out here and see what you're looking at. Angle H is an inscribed angle because H is a point on the circle. Well, then look over here, and if I knew what the measure of arc JK was, finding the measure of angle H would be easy. We just did some problems like that. And then look at angle G here. It's also an inscribed angle because G is on the circle. And notice that both of those inscribed angles intercept arc JK. So according to our theorem, since those two inscribed angles intercept the same arc, those two angles are congruent to each other. So if those two angles are congruent to each other, doesn't that mean that the measure of angle H equals the measure of angle G? And now we can solve it for x. Okay? So if I subtract 2x from both sides, I'll get negative x equals negative 54. then if I multiply both sides by -1 or divide both sides by -1, x equals 54. The question asks us to find the measure of angle h. Well, the measure of angle h is x. So the measure of angle h is 54. All right. Y'all still hanging in there with me? Okay. Do number 6. And does your work look anything like my work? So look, we can make these problems as difficult as we want, can't we? By making the equations tough to solve. But here's the thing. Shouldn't we be able to solve pretty much any equation thrown at us? Especially if we don't put in exponents and we don't put in two different variables, any just what's called a linear equation with just an x, we ought to be able to solve it. I don't care if they put decimals, fractions, whatever, we ought to be able to solve it. All right. Any questions? Okay, what else then? Well, triangles and quadrilaterals that are inscribed in circles have special properties. And let's see what they are. An inscribed angle of a triangle intercepts a diameter. Now, we haven't talked about intercepting anything besides an arc so far. So, if an angle is going to intercept a diameter, if I were wording this, I would have said just that, probably intercepts a semicircle. But I get the book's point because diameters and semicircles go together, don't they? So when they say intercepting a diameter, it's the same thing as intercepting a semicircle. It's just that semicircles always have diameters that go with them. Diameters always have semicircles that go with them. So an inscribed angle does this, intercepts a diameter or a semicircle, if and only if the angle is a right angle. Now, we could actually live without this theorem because what's the measure in degrees of that semicircle? 180. So wouldn't the inscribed angle be half of 180? So that's 90, okay? But a few days ago, and I don't remember the context exactly, we had to know that when we had a triangle and one in the hypotenuse, well, one side of it was a diameter, and I said, we know that's a right angle, and one of these days I'll tell you why. That's why, okay? If one of the sides of the inscribed triangle is a diameter, then the angle opposite that must be 90, which means we have a right triangle, okay? So it works both ways. If you see that it intercepts a diameter, the inscribed angle has to be a right angle. If you have an inscribed right angle, the side of the triangle opposite that must be a diameter. Okay? Number 8. This time we're supposed to find the measure of angle R. Well, look what we've got. We have segment PR that's a diameter. An angle Q is an inscribed angle, because Q is on the circle, that intercepts this diameter. So angle Q has to be a right angle, which means triangle PQR is a right triangle. Well, that gives us a way to solve for x. Now, I could say 3x plus 1 plus 90 plus 7x minus 1 equals 180. But don't we know that the acute angles in a right triangle add up to 90? So let's do that. So 3x plus 1 plus 7x minus 1 equals 90. That'll be 10x equals 90. Oops, x doesn't equal 90. So x equals 9. And if x equals 9, the measure of angle R will be 7 times 9 minus 1. 63 minus 1 will be 62. Now let's take a look at number 9. We know that angle M is a right angle, don't we? So that makes LMN a right triangle. Hey, since segment LM is congruent to segment MN, what kind of a right triangle is this? It's a 45, 45, 90. It's a right triangle and it's isosceles. The only kind of right triangle that's also isosceles is a 45, 45, 90. So they want us to solve for x. That angle right there is 45 degrees. Now, could I solve it essentially the way I did number 8? I could, because I could say, oh, okay, base angles are congruent, so this one's also 2x minus 5, and add those together and get 90. But notice that it's a 45, 45, 90, and all I've got to do is 2x minus 5 equals 45, so 2x equals 50, and x equals 25. So on problems like this, we need to recognize when we have a right angle, we need to recognize when our inscribed angle is a right angle, and then we know a lot about right triangles, okay? So they could, or I could, or the ACT could ask you some fairly difficult questions out of this, couldn't they? They could expect you to use the Pythagorean theorem, your special right triangle facts, trigonometry. So there's a lot of different things they could throw in at us besides just remembering that, oh, if the inscribed angle intercepts a diameter, it's a right angle. Okay? Now, we said something about quadrilaterals as well. It says, while many different types of triangles, including right triangles, can be inscribed in a circle, only certain quadrilaterals can be inscribed in a circle. Okay? Because you can make any shaped triangle inscribed in a circle that you want to. All right? But not so much with quadrilaterals. If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. Opposite angles, not congruent, not a parallelogram. Opposite angles are supplementary. And I can show you why. This isn't a proof, but this is just here's why. Here's angle K. It's an inscribed angle. It intercepts that arc. Angle M is the opposite angle in the quadrilateral, isn't it? Well, look what angle M intercepts. So altogether 360 degrees was intercepted, correct? By two inscribed angles. So doesn't that mean that the measures of the inscribed angles put together should be half of 360? Because the measure of an inscribed angle is half the measure of the intercepted arc. So if 360 degrees are intercepted, then the measures of the angles total up to 180. Well, and if angle K and angle M add up to equal 180, we call them supplementary. So in an inscribed quadrilateral, opposite angles are supplementary. And again, not a proof, but there's why. And let's see how we're going to use that. Number 10, they want us to find the measure of angle C and the measure of angle D. Let's find C first. So here's angle C. It's an inscribed angle, and it's an angle of an inscribed quadrilateral. Here's angle A. It's an inscribed angle, and it's an angle of the inscribed quadrilateral, and it's opposite angle C. So according to our theorem, angle A and angle C are supplementary. So 2x plus 58 equals 180. All right, so what's 180 minus 58? Is it 122? And then what's half of 122? All right, now, that's not the answer, though, is it? The measure of angle C. Oh, you know what? I should have stopped right there, shouldn't I? Because the measure of angle C is 2x. I've already got it. Measure of angle C is 2x, so it's 122. I didn't even have to actually know what x equaled. Okay. Then they want us to find the measure of angle D. Well, I'm not going to draw it all out. I think you can see it. Angle D and angle B are opposite angles of that inscribed quadrilateral. So they're supplementary. So 3y plus 4 plus 2y plus 16 equals 180. 3y plus 2y is 5y plus 20, 180. 5y equals 160. Let's see, y going to 16. That'll be a big 3, 32. All right. Then the measure of angle D will be 2 times 32 plus 16. So that'll be 64 plus 16. That's right about 80. All right. Questions? Okay. Now, as you're working through the assignment I'm about to give you, I want you to realize something. I think, of course, I've been doing this since, for twice your lifetime. I think each section we've done is maybe not easy is the right word, but not real complicated. What gets complicated about circles is that we don't work with circles very much. All right, you spent a lot more time in middle school with rectangles and triangles than you did circles. We've spent all year up until now without hardly ever talking about a circle. Everything starts looking alike if you're not careful. Don't confuse inscribed angles with central angles. Don't forget about how chords also intercept arcs. So because arcs get intercepted by 3 different things now for us: central angles, chords, and inscribed angles. And they all work just a little bit differently. So when they all get jumbled up together, like on a quiz, it can be a little bit taxing sometimes to keep it all straight. So make sure you're keeping it all straight, okay? And here's your assignment. On page 713, do 1 through 6, 8 through 20, 23 through 30, 32 through 36, 42 through 46, and 51 through 54.